So we're well into magnetic fields now, and let's do a quick recap of what we have. We have the ability to calculate the magnetic field due to a single charge. We have the ability to find the magnetic field due to a current of charge. And you know what that reminds me of? That reminds me of when we did the electric field of first a charge and then a continuous charge distribution. We went from using a simple Coulomb's law, well, that one was for the force, but the E equals kq over r squared formula for a point charge, to using the integral form. And we quickly realized that there were limitations to the integral form as far as our own abilities to be able to solve it. And we came up with a different approach to solving those continuous charge distributions when there was a high degree of symmetry, and that was Gauss's law. And now the question we have to ask ourselves is there a method to solving these current carrying wires magnetic fields other than the Biot-Savart law, using the integral method that was taught before? And the answer is yes. There is sort of the wire equivalent, or the magnetic field equivalent, of Gauss's law, and that is known as Ampere's law. So we have Ampere's law. Now I know there's an accent on this E, but I always forget which way it goes. Is it that or that? I'm going to keep it as that. And so Ampere, or Ampere's law, is going to give us a way to calculate the magnetic field from a current carrying wire without having to resort to the Biot-Savart law. As we saw with the Biot-Savart law for current carrying wires, we only were able to do it when we had a constant theta. And usually that theta ended up being something that made our problem very easy to solve. But we'll find that with Ampere's law, we can do it for different types of wire distributions that will be more useful for us. And so I'm going to actually go ahead and write down Ampere's law rather than deriving it. And the reason is that I had spent, I don't know how long it took me, hours, right? Over an hour certainly, to derive Gauss's law in a previous video. And the derivation would be a bit repetitive. And so instead of just doing that, I'm going to give you the formula, and then we're going to break it down. Ampere's law says that B dot ds is equal to mu naught I enclosed. And when I look at that equation, there's something very, very familiar about it. I certainly see some similarities between it and the much more familiar Gauss's law. And so let's write Gauss's law down. We should actually label this as Ampere's law. And remember Gauss's law simply said that the integral, and remember that circle around the integral indicates that it is a closed integral, and we know that that meant that our surface had to be closed. This time I don't have an A there, I have an S there. So I'm going to have to understand what that means. And this was equal to Q enclosed divided by epsilon naught. And so there are certain similarities, absolutely, right? Let's break it down a little bit just to see what is in common between the two of them. So in one I have the magnetic field, and the other one I have the electric field. That's eventually what I'm usually solving for. In some cases you are given those values and looking for something else. That seems very equivalent. Then I'm taking the dot product of that with ds here as opposed to dA. If anything, that seems easier. I'm certainly much more comfortable and used to taking the integral of a one-dimensional thing, that is a line like an S usually represents, than I am the A, which was an area. And so remember, for Gauss's law, we had to construct a Gaussian area, that's it, a Gaussian area area that surrounded our charge. This time we're not going to need a surface. We're going to instead create a line or a ring or a path, if you will. So instead of a Gaussian surface, we'll have an Amperian path. And we'll see that when we get to it. Let's look at the other side of it. We've got our Q enclosed over here that showed us how much charge was inside our Gaussian surface. And we can compare that to I enclosed. And again, we have the enclosed term here, meaning that our current I is going to have to be inside whatever this is. It's going to be the amount of current inside that Amperian path or whatever it ends up being. And then other than that, we just have constants indicating what is happening, whether it's electric or magnetic. All right. So I'm feeling pretty confident. I don't know about you, but I'm feeling pretty confident about this equation, B dot ds equals mu naught I enclosed. Let's go over each of the terms to make sure we understand them. B, again, the magnetic field. S is going to be ds is going to be some path length element, some teeny little piece of a path. We take the integral S, it should be the entire path. We've got ourselves the constant mu naught, which we already know, and our I enclosed, which is the charge enclosed. Now, I want us to remember what we did when it came to our current. When we were doing our Gauss's law for different charges, we had to take into account different types of surfaces that we could encounter and volumes, etc., whether it was a sphere, a cylinder, a plane. Now we don't have to worry about any of those things. When we're doing current carrying wire, we're almost certainly talking about a very similar orientation, probably a cylindrical wire, and we're trying to calculate the magnetic field coming off of that wire. And even in some cases, it doesn't really need to be cylindrical, as you see. But regardless of that, what I'm basically saying is there's not like a whole bunch of different shapes that you're going to be encountering while you're doing Ampere's law. It's just wires. It's only wires, current carrying wires. So let's write some stuff down about all of this. Oh, let's get a pen. When using our Ampere's law, to find the magnetic field B, due to some current I, the one mystery element here is ds. And you have encountered a ds when you did the Biot-Savart law. When we did the Biot-Savart law, the ds, if I recall, was a teeny little length of the wire itself. Here it is not that. Traditionally, we still use ds, which is a little bit disappointing because both of these have a ds that stands for something different. ds in the Biot-Savart law was a line segment, a little tiny piece of the wire itself. But this is what ds is here. It's going to be a small path length element. Segment or element is fine. Of a closed loop. All right, so I'm giving you the shape of ds. I'm giving you the shape of every Amperian loop you do. Remember when we did our Gauss's law, E dot dA, you had to come up with your own surface, and then you had to find the area of that surface. Sometimes it was a sphere, sometimes it was a cylinder, it was a box, all kinds of different things depending on the electric field coming off of the charge distribution. Now we have a very simple, or I should say, we only have one possible outcome, and that is of a wire, and we're going to be creating a loop around that wire, a closed loop, a one-dimensional length. and ds is going to be a tiny little piece of that length, where s represents the total length. And let me just be very, very clear that this is not the same ds as we saw from the Biot-Savart law. All right, and so let me also write down, as I was saying, recall, in Gauss's law, we chose a closed symmetric surface. And remember that that symmetric surface went through the point we were trying to calculate the electric field of. So recalling, in Gauss's law, we chose a closed symmetric surface. Now, in Ampere's law, because we have ds and not dA, you're going to choose a closed symmetric path. And since it's closed, maybe path is not the best word, but rather loop or ring, etc. And remember, it must go through the point we want to find the magnetic field. Go through the point where we want to find the magnetic field. All right, so let's make sure we got all that. So recalling Gauss's law, we chose a closed symmetric surface. So if we had, let's say, a sphere of charge, we chose a symmetric sphere around that charge. Now in Ampere's law, we're going to have this wire, and I want to choose a path or a loop that goes through the point where we want to find the magnetic field. Now, it should still be symmetric around that point, okay? We're not going to make some strange path, hexagon, or you know, an oval where it's kind of not really in the middle. Of course, when we have a cylinder, we're going to choose a circle. We're going to choose a circle that is a symmetric loop around the cylindrical wire. And so what that means is, to solve this problem, we must draw an Amperian loop. Please note that I don't believe the word Amperian loop is actually commonly used. I may have made that up, but I like it. If I'm going to talk about a Gaussian surface, which is the common vernacular for that term, I think an Amperian loop helps us to understand what we're talking about a lot better. So we must draw an Amperian loop around our current, which must be a circle for a cylindrical wire. If we have a cylinder like so, clearly a circle is going to be able to surround that cylinder symmetrically. It must be a circle, and that circle should have the same center as the cross section of the cylinder. Okay, so why don't we do sort of a generic example of an Ampere's law problem just to get us started, and we'll do more examples in a future time. So what is the magnetic field? Created by a long straight wire at a distance b above the wire. And let's give a current here. The wire has a current I to the right. Okay, so all I'm giving you in this problem is the current through a wire, as well as where the location that we're trying to find the magnetic field is, which is some distance b above. I mean, that sounds kind of familiar. I feel like I've done problems like this for the electric field. Oh yeah, it does kind of look familiar, doesn't it? But in those days, we just had a line of charge, and those charges weren't actually moving. But now we have to have them move. Remember that the only way to create a magnetic field is to have a bunch of charges that move. And so within our wire, we imagine there are many, many charges, and that they are flowing, creating a current, and that current is creating a magnetic field, and we're going to calculate that magnetic field at the point P, which is a distance B above the wire. Okay, here we go. Now, one thing to think about before we get started is, could we solve this using the Biot-Savart law? Could we use the Biot-Savart law to do this problem? Because I know how to use the Biot-Savart law. And the problem with that method is that the angle would not be constant. Remember that in the Biot-Savart law, the angle theta is between ds, which is in the direction of current, and r, which is r hat, which is the direction of the point P. And so they're going to constantly change as we go around this wire segment, and it will get exceedingly difficult to do. And we don't need to worry about that because we can do it with Ampere's law. And so let's go ahead and figure out how to do this problem. I'm going to start by writing down my equation, choosing to use B dot ds equals mu naught times I enclosed. Means that I need to start with a dot product. I've got a dot product. Whenever I have a dot product, that's the first thing that I want to do to get rid of the vectors for one thing. And I write B ds cos of the angle theta. All right. So I've got to pause here for a second to make sure I understand what each of the terms are. And I think I'm going to draw the theta and I'm going to draw the ds just to make sure that I get what's happening here. And so I will redraw my problem. I don't want to touch the original question. And so here I am redrawing it. All right, it looks identical. Wow. And what I'm going to do is to draw my Amperian loop. I probably should have done this to start with. Just as with Gauss's law, we drew our path first. Here we have to draw our Amperian loop. And so let's get started and draw it first. That should be the first step, just like it was from the Gauss's law. But I wanted to show you what I need to find out. And so let's go ahead and draw this circle. Wow, that looks amazing. And that circle completely surrounds my wire. It is symmetric around I, and it goes through my point P. So I'm good. And we will always use that circle to go around a cylindrical wire. The other thing that I'd like to see is how can I draw ds? And how can I figure out what the angle theta is? Well, I want to redraw this picture. I want to redraw this picture so that I can look at it from the edge. I want to take this wire here and I kind of want to look at it down this way. So imagine I look along the wire, and here I'm going to draw a little face. All right, so this individual is looking along the edge of the wire, and I'm going to redraw this circle. I just want to make sure everything is consistent in the diagram. It's pretty good, but I think this should be like this, and we'll make this disappear. There we go. Yes, I like that a lot better. Okay, so now I'm going to draw that same circle, but from kind of the edge on view. If I was looking through this wire in that direction, and I'm drawing it from that orientation, that wire is going to look like this. That's it. It's going to look like a circle with an X in it. Recall that that represents the wire going into the page. That represents current going into the page. And I'll put my point P above it here, and I'll draw that same circle. Symmetric around my wire. There we go. That's looking great. And remember that this distance here is B. Okay, so now what I want to do is to draw my ds and perhaps even give the direction of B so that I can figure out the angle between ds and B. So this whole circle here, this fake Amperian loop that I have created, is S. It has a length S. It is a closed circle loop. ds is a tiny, tiny, tiny little piece of that circle. And I'm going to represent it here. That little piece of the path is ds. And the definition of the direction of ds is tangent to the circle. By its definition, it goes tangent to the circle. I will make a note of that at the end of this example. But that's the way ds goes. It comes off the circle tangent. Does it have to go this way? Could it go the other way? Yeah, it doesn't matter. It really doesn't matter. The magnetic field direction, on the other hand, we have to get from the right-hand rule. And this time we're definitely using our Amperian right-hand rule. The Amperian right-hand rule, since we don't have a cross product, means that we take our thumb and we put it in the direction of the current and figure out which way the magnetic field goes. And so let's grab the wire this way, and it looks like it's coming kind of out of the page. But if you were to do it in this point of view, now your thumb should be pointing into the page, and our magnetic field is wrapping around in this direction. And so in my page here, it's going to be going that way. Oops, let me get another color there. And I want everyone to check this for themselves. The magnetic field is going that way. Now, I know what you're saying, like, should the magnetic field be going around curved, like a circle around the wire? Yeah, absolutely. It should totally be in this direction, but we don't care about it everywhere. we're only drawing it at ds. We're only drawing the magnetic field at the point P. At P, it's tangent in that direction. And so the angle theta between ds and B should be 0. The angle between ds and B is 0, and it's going to be 0 whenever we have constructed a proper Amperian loop. Because by its very definition, the direction of ds is tangent to the circle, but if we've set up the proper circle, then the magnetic field will also be tangent to that circle. So 100% of the time it will be 0. I mean, it could be 180 as well, right? You could have had ds going the other way and B going this way. That doesn't matter because the cosine of either of them is going to have a magnitude of 1. And that's all we're going to use to solve the rest of the problem. All right, so let's go ahead and continue the equation. Now that I have calculated our angle, we can go back to the integral of b dot ds. Oh, sorry, not b dot ds. We've already got rid of the dot. We have b ds cos of 0. And all that is equal to mu naught times I enclosed. Cos of 0 is 1. Guess what happens to the b in the integral? Just as the e was able to slip out of the integral because it was independent of ds, or dA in that case, b is independent of ds and comes out of our integral. And finally, what is the integral of ds? That's right, just s. And so the left-hand side becomes bs. That's right, it's totally bs. And it is equal to mu naught times I enclosed. So remember what each of the terms is. B stands for magnetic field. S is the length of our Amperian loop, not the wire itself, times mu naught times the current enclosed. And how much current is enclosed in this case? All of it. You can come up with problems where not all of the current is enclosed. For example, if you were trying to find the magnetic field within a wire, you can actually use Ampere's law to do that, but that's a more complicated problem that we will deal with another time. So S is the length of the Amperian loop. Now, let me be straight with you for a second. In this class, in first year physics, you will, once you choose that you are using Ampere's law, you will always start with this equation. Then, through taking the dot product, finding the angle, you will always end up with BS. Always, always. But you have to be able to show the steps. You have to understand how you get to this stage, but you'll always get there. You'll always get there. And so let's put in our formula for S. We know that S is the length of that circle. We knew the radius of the circle was B, and so 2 pi times the radius gives us our S. Now, I like to always put in the S equation before moving it to the other side, because again, the left-hand side is all about the Amperian. The right-hand side is all about the wire itself. And so this side stays as mu naught times I. And we can rewrite B as mu naught I divided by 2 pi B. That looks good, except we're just missing one thing. Of course, the direction. We need to know which way our magnetic field is going at the point P. We should do it for our original problem, the way it was originally presented. So if you would do me the favor of raising your right hand, everybody raise your right hand, face the screen here, and have your thumb pointing in the direction of current. So we're pointing in the direction of current, and we see which way our curled fingers are going. So the curled fingers are going around like this. They're going around like this. But where's the point P specifically? At the top, at the top. And so if my thumb is this way at the top, my fingers are pointing out of the page. Out of the page is right. That's good, and we will do additional examples of Ampere's law another time. Now that we've looked at magnetic fields, what they are, how to calculate them both in magnitude and direction, a number of different ways, it's finally time for us to talk about magnetic forces. And again, this is backwards as to how we did it with electric fields. Recall with electric fields, the force was introduced before because we didn't really understand the electric field at the time. Now we have a very good understanding of fields, and so we introduced a more fundamental magnetic field. We're good with that. Let's talk about magnetic forces. And we're going to start with the magnetic force of a point charge. Now, since we already have established how to calculate the magnetic field, let's calculate what happens to an object that's feeling the magnetic field, if you will. Basically, what I want us to do is to create the magnetic version of this equation. F equals Q times E. So if you remember this equation up here, F equals QE, that gives us the force on a charge Q in an electric field E. And so the question is, can we create another equation similar to this? Now, I wonder if F equals QB will be enough. If we put a charge in a magnetic field, will it feel a magnetic force? What do you think? I think not. Given the necessity so far for having velocity be part of our work, that we have been requiring charges to be moving to produce a magnetic field, it stands to reason that the same thing is going to happen with our magnetic force. And so the magnetic force equation actually ends up being Q, so this is the charge in the magnetic field, but it also has the velocity term V in it as well. And we end up with this equation. The force is equal to QV cross B, where the field B is already produced. We're creating we're adding a charge Q to it. And if that charge Q doesn't move, it does not feel a force. It's just sitting in the magnetic field and there is no force. But if the charge is moving, then it will feel a force. That's interesting. That's actually very, very interesting. It makes me wonder which direction the force is acting on our charge. Because if I have a charge here and I start moving the charge in a magnetic field, is it going to feel a force in this direction? Is it going to feel a force in that direction? Well, that would be very, very odd. What we're going to find out is that it actually feels a force perpendicular to those directions. And so let's write down what all of this is. This is the force felt by a charge Q that is moving with a velocity V in a magnetic field B. So the force felt by a charge Q that is moving with a velocity V in a magnetic field B. But I want to break it down. I want to really start to understand this formula a little bit. Let's start with the magnitude. If we were to find the magnitude of that force, we'll throw our magnitude signs around both sides of this equation, QV cross B. And we'll take the magnitude of the cross product there. Left-hand side is obviously, we'll just call it FB. The right-hand side, we keep the magnitude sign on Q. The charge can be negative or positive. Doesn't matter. I'm just trying to find out how big FB is as a positive value for now. Multiplied by the velocity, multiplied by the magnetic field, and of course we still have the sign of the direction. When that, of course, is the direction between the two of them. Okay, interesting. So that'll get me the magnitude. If I want to find the direction, what do I use? Well, I'll use my right-hand rule. We have a classic equation that is a cross product, and the answer is also a vector. We'll get that from the right-hand rule. Let's practice the right-hand rule for this type of situation, just so I can understand the direction of the force. I'm really curious to see which way the forces are acting. So let's try a couple of examples, but we're just going to really focus on direction for now. Later on, we'll do a problem with values in it. So let's take a charge, a positive charge that is, and we will have an initial velocity in that direction. And we're going to have our magnetic field lines go this way. I don't want to go through it. Let's have it go like that. There we go. All right. And so that is B. And we're good to go. All right. What is the question? I want to know, what is the direction of the force on Q? This is our charge Q. All right. So how am I going to do this problem? I've never done a directional problem for the force before, but I can get the direction to any vector that is the cross product of two other vectors where I know their direction. And so let's go to our formula and check it out, make sure we understand. So V is in front of the cross. That's going to be our fingers. B is behind the cross this time. Okay, that's unusual, different than it's been before. Remember, B used to be our thumb in the Biot-Savart law, for example. But this is not the Biot-Savart law. This is the force law. And here, B is your palm, as if there's an arrow coming out of your palm. And now our answer is F. That's going to be our thumb at 90 degrees. Make sure you can make that nice straight 90-degree angle between your fingers and your thumb. Q could be positive or negative, so keep your eyes out for flipping. All right, here we go. Fingers in the direction of B, and so my fingers are going that way. My palm is in, oh wait, I forgot the formula again. Okay, V comes first. Okay, so here we go. We're going to put our fingers in the direction of V. All right, V is going down like so. And now my palm has to be pointed in the direction of B. Okay, this is hard to do. It's hard to do. Okay, there I go. There I go. Well, maybe like this. Is that good? All right. So now I'm pointing in the direction of B according to that. And finally, I extend my thumb 90 degrees and it's pointing into the page. Into the page is correct for the direction of the force. Interesting. So force is into the page. You can write into the page or you can demonstrate it like that. That is fascinating. So the force is actually 90 degrees away from the velocity. So even though that velocity is going down, the force, which will result in an acceleration, the net force on this is going to be equal to mass times acceleration. It's going to have a velocity this way, but an acceleration into the page. The subsequent motion will be quite interesting, and we will investigate that a little bit later. Should we do one more? Sure. Let's try the following. This time I'm not going to make it hard. This is basically as hard as it can possibly get. I'm going to give you a negative charge. And I'm not going to tell you the direction of the velocity. I want you to find the direction of the velocity if the force on the charge is going this way. So I'm giving you the force this time, and I'll give you the direction of the magnetic field as well. So that's my magnetic field, and this time your question is, what is the direction of velocity? And this isn't the direction of the velocity due to the force or anything like that. It was the initial direction, sorry, the initial velocity of my charge is just an unknown, and I would like to know what it is. All right, so we're using the same right-hand rule. Again, your fingers are V, your palm is B, and F is your thumb. Now, when the answer isn't your thumb, you can just kind of use trial and error to make sure you get it right. And so it looks like I've got force in that direction. I've got my palm up. That looks good. Pointing up. And my fingers seem to be out of the page. So is the answer out of the page? No, think a little bit more carefully about it. That's a negative charge. A negative charge. Well, when I have a negative charge, I definitely flip my force 90 degrees. Let's see what happens when I flip my fingers 90 degrees. So I think the answer could be into the page again. Let's find out. So I'm going to have my fingers into the page, my palms pointed up, and my thumb comes out to the right this time. But because it's a negative, I flip it, and it is going that way to the left. So that is correct. The direction of V should be into the page again. Cool. All right. And you'll get lots and lots of practice with that. Before doing any other numerical example, I would like to introduce the force not just on a charge experiencing a magnetic field. What happens if I have a lot of charges and they experience a magnetic field? Namely, what I'm talking about is, of course, a current carrying wire. It makes sense. If a single charge with a velocity is in a magnetic field, it feels a force. I just found out what that force was in the direction of that force. If I have a current carrying wire, well, it's just a whole bunch of charges with some velocity. They are, of course, going to have a force as well. And so let's figure out what the force on a current carrying wire is. All right. So I'm actually going to start by writing down the formula, and then we're going to break it apart. And the formula for the force on some wire is going to be I, the current through the wire, L, the length of the wire that's experiencing the magnetic field. Sometimes a wire can be longer than the magnetic field area itself. So this L represents the length of the wire in the magnetic field only. Cross product with B. So IL cross B. That's very, very consistent with what we saw up here with QV cross B. Q and V are a combination of I, and now we have our length in there as well. And that will give us our force. Now, when you look at that, you're saying, okay, it makes sense. I know what F is. I know what I is. I know what L is. I know what B is. But why is L wearing a hat? Why does L have an arrow vector on it? How does the length have a vector? Well, go ahead and guess what the direction of the length is. Go ahead and take a guess what the direction of L is. We've seen this once before, where the ds in the Biot-Savart law didn't seem like it should have a direction, but it did have a direction. That direction was the direction of the current. And the same thing happens here. L is going to give us the direction of the current. I itself doesn't want to be a proper vector, so we force L to be a vector in its stead. This is the force on a wire with current I and length L. And in brackets, let me know it need not be the total length, but the length experiencing the magnetic field. Let's say length in the magnetic field. And so the force on a wire with current I and length L in a magnetic field B. That's pretty funny actually. Because I'm just thinking about a wire and how does a wire feel a force? We understand how a charge feels a force. Charge is a mass, it has therefore an acceleration, it's going to move because of the force. What is a force going to do to a wire? Well, it's also going to apply an acceleration, but what it could do is it could deflect. We'll do an example where it could actually counter the effects of gravity itself. And so it's a very, very similar thing. Let's write down what that length vector was, because that is a bit peculiar. This length vector is the length of the wire again within the magnetic field and it has a direction given by the current flow. All right, so if we want to calculate this in some example, and this will make a nice, interesting problem for us to do. We'll do an example in short order, but let's calculate the magnitude in general. So I've got a cross product of IL cross B, and to calculate the magnitude, I'm going to multiply by I times L times B times the sine of the angle between the current direction and the magnetic field. And so we'll get some experience getting that angle and eventually getting that value, while the direction is once again given by our general right-hand rule. The general right-hand rule is just the one that's not Ampere's right-hand rule. Okay. So let's do a fun example where we can not only see the effects of the magnetic field on a wire, but also help us to figure out the direction of the force. So I'm going to construct a table of magnetism. That sounds awesome. Here's a tabletop of magnetism, and we're looking down at the table, and the magnetic field in all of these cases, for the entire table, is going to be into the table. Like so. And we're going to get three separate wires through our table. So these holes represent holes in the table, and I'm going to run a wire through them. So they go from one to the next, from one to the next, from one to the next, like so. So I've got these three wires, and now I'm going to start to run a current through them. So we have the magnetic field, and through the first wire, I'm going to run a current of 0. And so I would like you to use the right-hand rule to calculate or to figure out what the direction of the force on that wire is going to be. Do that now. What's that? Oh, okay. You're saying there is no force on that current carrying wire because it carries no current. That's exactly right. So just like a charge that has no velocity, has no force on it in the magnetic field, if I goes to 0, the wire might be full of charges, might be full of electrons, but they're not going to feel a force because they're not moving. Without a current, you have no force, you have no direction necessary. And so for this, F is equal to 0. Okay, good. Got me. That was tricky. Try this one. Oh, you know what? Let me write the F equation right here because it can be cumbersome to go up and find it every time. And it's a new equation to us, so let's have it handy. This time, let's make the current coming down. All right, so there is our current through the wire. And I'd like you to take a second to calculate the direction of the force due to that wire. Do it now. Pause if you need the time. Okay, so let's start again with our right-hand rule. Fingers represent what's in front of our cross product. Looks like it's current, and so I have my I going down, right? Okay, I's going down, and my palm should be facing into the page. Oh, it's already doing that. That's great, because I don't want to twist that around. So I'm good right now, and I just take my thumb 90 degrees from my finger and see which way it's pointing. It is pointing to the right. The force is this way on that problem. And I know what's going to happen to my wire. If the wire isn't actually tight, you will literally have a deflection in the wire, like so. Let's redraw all this stuff a little bit neater. If the current is going down, our wire will deflect in that direction. And that's because the force is to the right. Okay, good stuff. You probably know what's coming next. I want the current as it goes up. And maybe you've guessed what the right answer is, but I want you to actually use the right-hand rule to find the direction of the force. Go ahead, take a second to do that. Okay, now what we have is the current going up. The magnetic field is into the page. Well, it's hard to do. It's hard to do. Maybe I'll stand like this. Okay, so it's going this way. Got my current up, got my magnetic field into the page, go 90 degrees. So this way, to the left. So the force is going to deflect to the left. The entire wire is going to end up going to the left, like that. And my force is that way. Okay, looks good. And so those will help us get all the directions. We're still going to need a little bit of practice for calculating the magnitudes and seeing what different types of problems we can encounter with this as well. But that will wait for another time. Now let's take what we've learned about forces, magnetic forces specifically, and do a very specific application with how we can manipulate charges in a magnetic field. And so this is an application of motion of a charged particle in a uniform magnetic field. And so this is going to rely on the equation that we presented earlier, specifically not the one for the wire, but the charge, QV cross B. That's our starting point here, because we want to talk about the motion of a charged particle in a uniform magnetic field. That motion is going to be a combination of the velocity V that it has, as well as the acceleration that results from this force FB. So we take FB, we equate that to MA, and we see what happens. Well, what have we learned so far about the direction of this force, this eventual acceleration in comparison to the velocity of our objects, the velocity of our charge? What we know, as I showed with the two examples we did for the charges, is that the magnetic field is always going to be perpendicular. That sign is the perpendicular sign. We can do a little better than that. Perpendicular to V. So those two directions are always perpendicular. Let's take a quick look to just jog our memory. That's exactly what we did here. You can see that velocity was down and F was into the page. Here we had F to the left and V into the page. Again, 90 degrees away from each other. And that's what we expect with a cross product. A cross product, the product is always going to be 90 degrees from the others. And so basically what we have is us trying to figure out what's going to happen to the motion of a charged particle in a field. Let's see if we can plot that out here. So let's pretend for a second that I'm a charged particle. I'm a charged particle and I'm going to walk in this direction. So my velocity is here. And let's say that the magnetic field is upwards. So if V is this way, and I'm positive, of course, V is this way, B is that way, and then my force is going to be out this way. So if I want to walk, or if I am walking this way, and something starts pushing me in that direction, what happens to my V? Does a force in that direction affect my velocity in this direction? No. I will continue to have a speed of whatever I have, but what is the force going to do? The force is going to make me go that way. Essentially, by combining whatever my velocity is and this force, I'm going to end up walking kind of like this. And my velocity will change. I'll start going this way. Eventually, I'll get to this position where my velocity is now going that way. Well, the right-hand rule says if my velocity is going that way, the magnetic field is still going up, my force is headed in that direction. And so now my force is that way, my velocity is that way. Which way am I going to go? I'm going to kind of go in this direction. And what my eventual motion is going to be is the following. Eventually, my force and my velocity will always be 90 degrees away from each other. And I end up doing this kind of motion. I don't have much space to do it here. It's not me spinning in a circle, it's me going around a circle. And so my velocity is always going to be tangent to that circle, and my force is always going to be pointing to the center of that circle. And I will demonstrate that with drawings very, very shortly, but let's make that observation. The direction of the force is center seeking. The FB direction is center seeking. A force that is always pointed towards the center. Oh man, what was that called again? Perhaps you remember from a previous course. But please note that this FB is always perpendicular to the velocity, and so it actually does not influence the speed. The speed of our object will remain constant, and that will be v. It will be v. The only thing that FB does is change the direction. So FB does not influence the speed, only the direction. All right, so let's draw it out here and see if we can understand this center-seeking sort of motion a little bit better. We're going to need this entire page. Let's create another tabletop. Another tabletop with a magnetic field, again going into the page. All right, I'm just going to draw the magnetic fields at the corner and get them out of the way, but this is a magnetic field that is equal across the entire surface, all right? Even though I will just put it at the corner. So that is my magnetic field. It is constant everywhere, but I want to focus on my charged particles. So let's have a positive charged particle and we'll give it a velocity. Let's start right here. And that charged particle has an initial velocity to the right. There we go. That's its velocity. Could everybody use the right-hand rule now and figure out the direction of the force for that v. Now you could do it to the screen, you could draw it on your piece of paper, just be a little bit consistent, okay? The one mistake that I sometimes see people making with the right-hand rule is they have a piece of paper here, but they're doing the right-hand rule in front of them, and they get a direction, and they might be like, oh, okay, it's up, but just make sure that you're doing it correctly. I like to do it on the piece of paper when I'm doing a test or an assignment type of question. But I'm going to do it over here for you. And so if we have our velocity in this direction, and we have the magnetic field going into the page, then my force should be up. Okay, that looks great. So force is up. In fact, let's make that one red. This is the force on the charged particle due to the magnetic field. And so, what is the combination of the force up and the velocity to the right? I expect it's going to start to move in this direction. And when it gets to some other point, then the direction of the velocity and the direction of the force change again and again and again and again and again, until eventually you're going to see that the charged particle has got up here now. Its velocity is now going to be pointing straight up. It's turned its direction because of that force. Well, now let's do the same thing again with our right-hand rule. V up, B into the page, FB to the left. Okay, FB is to the left this time. And we move again. And once again, our charged particle now ends up here as it continues to move direction. Its velocity is to the left. And guess which way its force goes? Check it for me. Go ahead and check it for me. But I'm starting to see a little bit of a pattern develop here where this force is going to be downwards. This is my FB. And finally, continuing on, the resulting motion changes direction and leads my particle down here, where its velocity is straight down, and the force once again can be easily found with the right-hand rule. It is to the right. And so all of these forces can be much better described as center seeking. Oh, and I missed the other charge. And so eventually it comes right back, exactly back to where it started. We're going to create this circular motion. And how long is this circular motion going to last? Forever. And is it going to, the radius of the circle, will it increase? Will it decrease? No, nothing. As long as the magnetic field is there, as long as the velocity of our particle remains constant, then you will have a perfectly circular path that our charged particle will follow over and over and over again. All right. So can we figure out some characteristics of this path? We sure can. We sure can, because what you're looking at is a centripetal acceleration. We are talking about a force that is center-seeking, that is not speeding up or slowing down our particle. All it's doing is changing its speed. All it's doing is changing its direction. Whenever you have a constant speed and a change in direction around a circle, we are talking about a centripetal acceleration. Let's recall that not only is FB equal to QV cross B, or here FB equals QVB sine of theta, we also have that the net force on the particle is equal to mass times acceleration. And that acceleration, since it is creating this circular motion, is our centripetal acceleration. Centripetal. And so we equate them together. We can say that our net force is equal to our magnetic force on our particle, that is. And so we'll put both of those equations together. Mass times centripetal acceleration is equal to QVB sine of theta. Does anyone remember the equation for centripetal acceleration? It's been a little while, but it is a very, very memorable V squared over R. Okay, interesting. Let's throw that in there. And we get mv squared over r is equal to qvb sine of theta. We can clean things up a little bit by realizing we have a v on this side, and we can cross it out with that v. So we're just dividing both sides by v. And the other thing we could do is the angle, because what is the angle theta in this problem? Going back, this is the angle between the velocity and the magnetic field. Magnetic field is into the page, velocity sometimes is left, right, up. That doesn't matter because it's always going to be 90 degrees in this case. And so let's sub this theta also for 90 degrees. And what is the sine of 90? I recall that is 1, leaving me with a much nicer equation which we could solve for any of these values. MVQB, but traditionally we write it in terms of R, the radius of the circle. R here should be equal to mass times velocity, all divided by QB. Interesting. This is a very, very interesting equation. What is so cool about this equation? Well, look at the factors in it. We have R, M, V, Q, and B. The mass and the charge Q are characteristics of the particle itself. B, the magnetic field, is something that we created. This is something that we put our charge into. So that's something that we should know the value of. In fact, we probably can control it. And then that just leaves R and V. And R and V are measurable values. So basically, at the end of this, this could be a method to identify an unknown particle. Imagine that you are doing some sort of physics experiment where you end up with an unknown particle. What kind of experiment sometimes has the result of unknown particles? Collisions. We could be doing collisions in particle accelerators where things are moved at high speeds and then they're slammed together at energies far, far greater than we're used to, and then some unknown particles can arise. If we throw those particles very quickly into a magnetic field and we watch the radius of the circle that is created, we should be able to calculate the mass and the charge, or at least the ratio of the mass and the charge of the particle, allowing us to identify it. And that's exactly what is done in a device called a cyclotron. But let's make sure we understand this equation first before we talk about that. So what this equation gives me is the radius of a charged particle Q with mass m and velocity v in a magnetic field. Good enough. All right. And so this relationship is used in a cyclotron in the following way. So that's what the application is all about. As used in a cyclotron, where our cyclotron frequency is given by the following equation. Omega is equal to V divided by R. Now, you're very, very familiar with omega. It's also known as the angular velocity. And so by its very definition, it's equal to V divided by R. But since R is just equal to mv over qb, we can rewrite this as qb over m. And so basically, we can measure the cyclotron frequency omega, and we can control B to again get the ratio of Q over M to identify mysterious particles, for example. We sometimes also make use of period when we talk about cyclotrons. And so the period of motion here is T equals 2 pi over omega. And if we substitute in our value for omega there, we have 2 pi m over qb. And so perhaps instead we measure the period of motion and again get that ratio of mass to charge. So let's just make a note of that. This relationship and device is used to measure, or let's say to identify, mysterious particles. And we will do an example of exactly that a little bit later. What we're about to do now is to introduce a solenoid. A solenoid is going to be an object that will prove very useful in many things that we do coming up. And so we can create a very, very simple solenoid by taking a wire, and what we're going to do is we're going to make loops in the wire. So we'll make a whole bunch of loops. This is harder than it looks. But basically, we're going to loop up the wires into a bunch of circles, a bunch of loops. And what I want to do is try to think about what the magnetic field through that solenoid is going to be. Let's draw a solenoid first. There we go. And we're going to run a current through that solenoid, just a wire that we looped up into circles around and around and around. And let's indicate the direction of the current right here. So it's going to go kind of like up that loop, if you will. And what is going to happen is that the magnetic field lines that are created by each of the wires are going to start to interact with each other. Now, when we have a long straight wire like this, it's very simple to know what the magnetic field directions are. They're just going, like if the current was going up, then the magnetic fields are just going around and around and around and around. But when you start creating these loops, then that magnetic field is going to get more complicated because it's going to start interacting with one another. Allow me to draw the net magnetic field of something like this. And I'll make sure I've given myself enough room for this picture. Make it a bit smaller. There we go. The magnetic field direction is going to look like this. And tell me if this seems familiar to you. In that direction in particular. There's more. Like so. We'll draw another one here in the middle. All going upwards inside and curving around back on themselves. That was maybe a bit too big. And one more. Just for symmetry reasons, we'll draw our last one like that. Okay, there we go. And so we've created this magnetic field through our solenoid, and it looks very familiar. This is the magnetic field that we first drew when we introduced the concept of a magnetic field for a naturally occurring magnet. And remember, for that naturally occurring magnet, we had a north and a south. So imagine a magnet that looks like this. With its north and its south, you're going to get the exact same patterned magnetic field. We'll have these magnetic field lines coming off of it in both directions. There we go. All right. And so what that indicates to me is that we have essentially reproduced the magnetic field that you would naturally get from an object like this artificially through electromagnetism. And so let's make a couple of comments about that. Whoa, 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 where did I go? No one panic, we got this. Just a little bit more to go. We'll finish it up just like this. As I was saying, I quickly wanted to note that closely spaced turns on a wire, basically how we've been describing what a solenoid is, produces a magnetic field similar to that of a bar magnet. let's say similar in shape to that of a bar magnet. Now I want to define something called an ideal solenoid. And an ideal solenoid is something that is more than just taking a piece of wire and twirling it around into a bunch of circles like we've been describing so far. This is going to be a very, very purposefully tight ring of wire that is going to have a much, much larger length than it does a radius of its turn. So it's going to be much longer than it is around. So the definition of an ideal solenoid as opposed to an ordinary solenoid is that an ideal solenoid is a solenoid with length much greater than the radius of its turns. And just to define those two values, if we go to this picture right here, and I will erase this in just 1 second, but just so we are all on the same page, the length here would be about that, and the radius would be that. Now, clearly the length is a lot larger than the radius, but not much larger, and so does not qualify as an ideal solenoid. The other thing we'll notice with ideal solenoids is that the turns are very tight together. And so let's give that a sketch. Let's draw a cross section of an ideal solenoid and see if we can learn anything interesting about it. I'll just move on to the next page to give my drawing enough room. The cross section of an ideal solenoid would look like this. It would basically be a stack of circles. But what you're actually looking at is the cross section of those loops, of the wires that make up the loops. And there'd be another one of these groups on this side. Like so. And so think about it. We've got the wires coming out of the page right here, and then going into the page. Oops. Into the page is given by the X, twirling around and coming out of this one, going back into this one, out of this one, into, out, in, out, in. And so what you're looking at is the cross section of basically looking at a solenoid where we're going to define this as our length, and our radius will be here. And again, it doesn't look much greater, but we're going to assume we go much further in that case. And the next thing we want to know is, what is the magnetic field, both inside and outside of the solenoid? Well, interestingly, inside the solenoid, you're actually going to get a perfectly straight, constant, uniform magnetic field. Let's see if we can draw one more line there. It doesn't look terribly uniform there, does it? Let's make it a little bit better. That's all right. And so this is our internal magnetic field in the solenoid. Let's call it B internal, as opposed to the external magnetic field, which is out here. And for an ideal solenoid, again, this is not necessarily perfectly true for a real world solenoid, but is our ideal version of one. We're going to have an internal magnetic field that's uniform, and the external magnetic field is going to be equal to 0, or very, very small, that we basically treat it as 0. And again, the length here is much, much greater than the radius, and so we're going to end up with essentially B external 0. And we can actually use Ampere's law. We're not going to drive it ourselves, but using Ampere's law, we can see that we can quantify that internal magnetic field in the following way. Turns out that the magnetic field inside an ideal solenoid is equal to mu naught, our usual constant, multiplied by capital letter N, which will be the total number of loops in the solenoid, multiplied by I, the current that's running through them. And again, even though it's not as obvious, there is a current running through them. That's what that dot and X indicate, that the current's going around and around and around and around, whether up or down. I did forget to write here that we're assuming that L is much, much greater than R. And let's finish up our equation. We got mu naught times N times I, all divided by L, the total length. Notice R does not play a role in here. As long as it's small enough, we don't have to include it. And this can be also written in the following way: mu naught times little n times I. Let's define both big N and little n, since those are the two values that are unique to the situation that we're talking about. Let's make sure we understand that big N is the total number of loops in a solenoid, while N is more like the number density. And so it's basically the number of loops per unit length. And so number of loops doesn't give us the absolute loop value or a number or the absolute length, but what it does give us is the number of loops per unit length. And that's the most important factor in determining what the magnetic field is going to be once we've taken into account our current. So magnetic field is just mu naught times N times I. And what we've done is we've got the magnetic field inside an ideal solenoid. And you're not going to be asked to derive this formula, but you will use it quite frequently.